Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through what we went through in week 3. So we went through the quotient rule, and then we also went through second derivatives and how that applies to graphing. So let's first look at the quotient rule. So you use the quotient rule when you have one function divided by another. Quotient means divided. So here u and v are functions of x. So u over v can be written as u times v inverse, v to the power of minus 1. If I apply the product rule to this formula here, I get this formula here. So the derivative of u over v is u dash v minus uv dash over v squared. So this looks a bit like the product rule, except there's a minus between, and you also have to divide by v squared. So let's look at the example here. So here we have a function of x divided by a function of x. We can't divide this and make this expression any simpler, so we need a rule that allows us to differentiate one function of x divided by the other. So we're going to differentiate this using this formula. So u is the function on top here, e to the power of 2x, and v the function on the bottom. So the way we do this, we differentiate the top. So the derivative of e to the 2x is 2e to the 2x. So that's u dash. And then I multiply it by v, which is the thing on the bottom, minus the thing on top times the derivative of the bottom. So the derivative of the bottom, v dash, is just 3x squared. And then on the bottom, we have the original function on the bottom squared, x cubed plus 1 squared. So now we're just going to simplify by factorizing the top. Notice in the top that each term has a factor of e to the power of 2x. This is like our first term, and this is like our second term. So what we do is we write that function out the front, and then we're left with 2 times x cubed plus 1 to get the first term, and then the second term is being multiplied by 3x squared. So I can't really simplify the top any further. Expanding the brackets won't make it any simpler, so I'll leave the top like that, and the bottom, x cubed plus 1 squared, I'll leave it like that. I am done. This is the derivative of this using the quotient rule. Let's now look at graphing. So let's look at graphing this function here, which is a polynomial. We learned how to graph trig and exponential functions last year, and calculus isn't always helpful. Like if you're trying to graph sine x or cos x, there's infinitely many turning points, so it doesn't really help. But if we want to graph a polynomial like this, we need to find the three things: y-intercept, x-intercept, and turning and inflection points. So finding the y-intercept is easy. You just let x equal 0. So here, if x was 0, we'd get y equals 0 times minus 2 cubed, which is 0. So the y-intercept is 0. This passes through the origin. So to find the x-intercepts, don't worry about doing polynomial long division or whatever. You can either use your graphics calculator, or if it's given in factorized form like this, you can just read them off. So if it's factorized, remember Null Factor Law says either the first thing equals 0, so the first x-intercept is 0, or the second thing is 0, which would mean x equals 2. Either way, you can use a graphics calculator to get x-intercepts because we're more concerned with the calculus. That's the point of this course. So now we're going to go and calculate the turning and inflection points. So turning points and most inflection points occur when the first derivative is equal 0. They're called stationary points. So after you've found where a stationary point is, you need to classify it. Is it a minimum, a maximum, or an inflection point? And this is the second derivative test. If second derivative is positive, it's a minimum. If it's negative, it's a maximum, and so on. So we need not only to find the turning points, but classify them. And we just need to be aware that not all inflection points are turning points. Not all inflection points are stationary. Inflection points occur when the second derivative is equal to 0. And you'll see in this one, there's actually an inflection point that's not stationary. So to calculate the turning points, we're going to calculate the derivative of this function. We need to know how to do this by hand and not just use our graphics calculator, because calculus is the point of this. So for the derivative of this, I'm going to use the product rule. So derivative of the first times the second plus the first times the derivative of the second. The derivative of the second function here is just 3x minus 2 squared using the chain rule. So the reason we practice factorization, it's hard to find the turning points when it looks like this, but what we're going to do is factorize to make it easier. You see, this term here and this term here have a common factor of x minus 2 squared. So I'll take that out the front. So now I need to say, what do I times by x minus 2 to get this first term? Well, it's being times by another x minus 2. That's how I got x minus 2 cubed. So x minus 2 squared in this term is being times by 3x. So I write plus 3x there, and then I'm going to collect like terms in the brackets. So now I have this. So if y dash is equal to 0, that's where stationary points occur, I have x equals 2. Or if this equals 0, I get x equals a half. So substituting each of these into the original function to find the y value, here y is 0, and here y is minus 1.6875. I'll just make it rounded up to 2 decimal places. So now, to classify them as maximum, minimum, or inflection, I need to find the second derivative. So I'm going to differentiate this, again, using the product rule. So to get this, I did derivative of the first times the second function plus the first, which is here, times the derivative of the second. The derivative of this is just 4. So now I'm going to factorize this. The common factor is x minus 2, and also there's a common factor of 2. So I take out my common factor, and then it's being multiplied by 4x minus 2 in the first one, and it's being multiplied by 2 outside of x minus 2 in the second. So then what I do is I expand this bracket here and collect like terms. And so I get in here 6x minus 6. So now I've found the second derivative. I can substitute in each of these points to see whether they make it positive, negative, or whatever. So if I substitute in x equals 2 into the second derivative, I get the second derivative is equal to 0. So this point here is an inflection point. That's because second derivative equals 0 at x equals 2. But if I substitute in x equals a half, then it will make this second derivative positive. So that means that this point here must be a minimum. So I've found and classified the turning and inflection points. But note here, if the second derivative is this, it will equal 0 when x equals 2, so that's one inflection point, I already knew that. But also, if 6x minus 6 equals 0, then x equals 1. So at x equals 1, there is another inflection point. But remember, x equals 1 was not a stationary point. That means x equals 1 is a non-stationary inflection point. Now, if x equals 1, then y equals minus 1. So that's my non-stationary inflection point. So what am I going to do with all this information? Well, let's just plot it. So I plot my y-intercept and my first x-intercept there. Now, x equals 2 is also an x-intercept. We know we have a minimum at half minus 1.69. So that's, about there. I'm just going to estimate it. And we know we have an inflection point here and an inflection point there. So what's the graph going to look like? So because this here is a minimum, we're going to go up afterwards. The curve is going to be concave up. But here at this non-stationary inflection point, remember at inflection points, the curve changes concavity. So it's gone from being concave up, now it's going to be concave down until it gets to x equals 2. So x equals 2 is a stationary point, but also an inflection point. So it's going to go like this. It's going to go up afterwards. There are no more stationary points, so it'll just keep going up like that. On the other side, this was a minimum turning point, so it's going to go the other way. It's going to go through the origin. There were no more turning points, so let's just keep going forever in that direction. So when you graph, just make sure that things are labeled so it's clear what the function is and it's clear where all the turning points and intercepts are. All right, thank you so much for tuning into this video. Sorry it was a long one, but keep your head up. You're doing a great job. This has been the luckiest maths teacher in the world. Have a great day.